My name is Zach Shvira-Conti, and I'm a research fellow at the Alan Turing Institute in London. And I would also like to introduce the co-organizer and colleague of the seminar series, Andrea Pizzaferrato, who is on the call with us, who is a visiting academic at the Turing. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. On a side note, if any of you are interested in sharing your work in this series, please do get in touch with either Andrea or myself. So some housekeeping questions are preferably asked towards the end, unless, of course, our speaker for today has no problem with answering questions on the go. Now, without further ado, I'll invite Andrea to introduce our speaker for today. And with that, I thank you all.
Oh, thank you, Zach. So our speaker for today is Karan Taneja. So Karan is a postdoctoral research associate at the Command Lab, part of the Department of Aerospace and Mechanical Engineering at University of Notre Dame, South Bend. He embarked on his academic journey with a bachelor's degree in civil engineering from Delhi College of Engineering, followed by a Master of Science in structural engineering from Delft University of Technology. Last year, he was awarded a PhD at UC San Diego. He works at the boundary of engineering and computational biology, focusing on numerical modeling of biological tissues, with a particular emphasis on skeletal muscle. His research is at the forefront of integrating physics-informed machine learning techniques with traditional modeling approaches to study the way we predict and understand the motion of human musculoskeletal systems. He's passionate about exploring the complexity of material behavior and is an advocate for leveraging machine learning to enhance our understanding of complex materials. Thank you again, Karan, for joining us, and the floor is yours.
Thank you, Andrea, for that kind introduction. Good day, everyone, and thank you for joining me wherever you're logging in from. As Andrea mentioned, I'm a postdoc at the University of Notre Dame. But the work I'm presenting here was mostly done during my PhD at UC San Diego, along with my colleagues Xiaolong He and Kai-Chi He, and my advisor, Professor J.S. Chen. So today I'm going to be talking about how we worked on the idea of developing these digital twin applications for the human musculoskeletal system, mainly by using motion capture data and muscle excitation data. And we developed two physics-informed machine learning approaches for it, which were the feature-encoded and multi-resolution techniques. And I'll be talking about that today. So before we really go on to the two approaches, it's important to understand why we care about this. So basically, forward dynamics is the process where your body transforms your neural excitation signals to the actual motion that you perform. So your brain sends a signal, your nerves pick up that signal, they hit the muscles, your muscles get excited, which are measured as a pseudo measure of the raw surface electromyography, which are these kind of sensors you attach to the skin. And they pick up these excitation patterns, which you can process to pick up muscle activation patterns. So how your muscles actually get activated. And it is these activations that ultimately lead to the force production of your muscles, which lead to your movement. So in inverse dynamics, we sort of study how this information is passed through the various length scales. So for example, right here, we are at the rigid body scale where this body is moving. If we zoom into your muscles, the first level we reach is the structural level. So at the structural level, your muscles are modeled as nonlinear spring damper systems with force length and force velocity relationships. That's a pretty simplistic form. So if you want to understand more about the body, we zoom in slightly more. We hit the continuum level, where we can include more physiological components into the mechanics of the problem, such as the muscle belly, the tendons, and aponeurosis, and other components which take part in the force transmission. And we can go down further length scales where we have the micro scale, and we can include other materials such as the extracellular matrix, which surrounds the muscle fibers, among other materials at the micro scale. And we can keep on going down further length scales if the problem needs to. But it's important to understand that together these systems ultimately lead to the production of motion. And if we understand these systems better, then it's more useful for us to it's useful for us to be able to predict motion, to really understand the muscle physiology during motion. And if we can somehow link them together, we can arrive at a digital twin for the human body. So really the question is, how is this information passed through these various length scales, right? Now, I have done work so basically we began our journey at the lower length scales, where we have a method to link and pass information between the microscale and the continuum scale. So we developed a multi-scale method for that, where we can homogenize the microscale properties to inform the continuum scale material behavior. And then we can localize this continuum scale deformation to understand the contribution of these various microscale constituents on the continuum scale deformation and force output. So this is where we began, but really like the focus of today's talk will be at the larger length scale. So at the structural scale, we developed machine learning algorithms where we use machine learning to identify parameters at the from the joint motion that we obtained from the subject. And then we used that trained neural network to be able to further predict the motion given the input. And using these two, we can do this. Using machine learning methods, we can do this simultaneously. So before we jump into the machine learning aspects, let's take a look at the physics of the problem at the structural scale. Now, we obtain these raw surface electromyography or sEMG signals from the sensors. And as I mentioned, these can be processed to obtain the muscle activation patterns. These activations drive the force production, so your muscles contract and expand, and that leads to the production of torque at joints. And that torque is what ultimately leads to the motion of the body. And that motion is modeled by this rigid body dynamics equation, where Q is our set of generalized degrees of freedom. The torque is basically a function of the muscle force. Sorry. And E is basically any external forces you apply to the system. So when we look further into how these muscle forces are produced, these are basically a set of homogenized nonlinear spring dampers with active and passive components in them. And these active and passive components, they are basically a set of parameterized systems of equations. So you see this parameter set kappa. The model that we use is called a Hill-type muscle model, and each Hill-type muscle model is parameterized by, for example, a set of 5 muscle-specific parameters. So, for example, we have the optimal fiber length, the maximum contraction velocity, and the maximum isometric force that the muscle can produce. The important thing to note here is that this is a parameterized system. So for each muscle that is involved in our motion, these parameters need to be calibrated. We can use the same set of equations, but we need different parameters for each muscle. And that is the challenge. So really, hence, for this inverse problem, we are given like a set of mixed frequency signals. We have the recorded motion data, and we have this raw EMG, which we further process. But basically that is our input, because like without troubling the subject, we can't really get more invasive measurements. So this is something we can get quite easily. So we know the motion, and we know our input, but we don't know the physiological and anatomical parameters. And usually optimization techniques are used for this sort of method. But the question we wanted to ask was, can we use machine learning to map these signals and also solve this inverse problem? Now, traditionally, we know that when we map an input to an output, machine learning is a bit of a black box. But once we use physics-informed methods to further supplement the problem, these can help in extracting these unknown parameters from the recorded data, and any mapping that we obtain should satisfy the physics of the problem automatically. So yes, physics-informed machine learning helps, but the crux of the problem really is mapping these mixed frequency signals. And that is what we set out to do. So the first approach that we had, the first set of approaches we had were the time domain and the feature-encoded training. And we worked on building this framework on the structural level. So basically, this is like a sample picture of the subject where we attached motion capture like apparatus to the joints. So the shoulder, the elbow, and the wrist. And we had like a huge setup here. All this data was was given to us by Professor Kenneth Lowe's lab at UC San Diego, who's really a master at all the motion capture stuff. And we attached sensors to the biceps and the triceps. So these sensors are basically Bluetooth-based, and they can capture these muscle excitation patterns quite efficiently. So the subject, you don't have to walk around with like a bunch of wires all around you. This is all like you just attach the sensor and like the computer picks up like your signal. So we obtained data for a simple elbow flexion and extension motion. And the physics of the problem was determined by this rigid body dynamics problem. So we had this bicep and tricep, pretty simple hill type model. And we then wanted to predict the motion for a signal which was not in our training set, and also identify critical parameters inside these bicep and tricep by using physics-informed methods. So approach 0, or like the base approach we started with, was the time domain training. So as the name suggests, you basically map the input sEMG, the raw sEMG, to the output at motion data at each time point. And in addition to the neural network parameters, we also had the parameters of the MSK differential equations inside the residual, and they were simultaneously minimized together with by solving this optimization problem. So like essentially just pick up like the time and the EMG data at each point from each muscle involved in the motion, and map it to the actual motion that happens at the joint. So synthetic tests did pretty well. So we have this set of 5 synthetic inputs and one like set of 5 corresponding outputs. And we trained on we tested on trial 3, and we trained on the rest. And the prediction is pretty good. And it also managed to identify the synthetic parameters quite accurately. However, this is where the trouble started, because we noticed that, like, if you look at the actual data, it's not smooth, right? The input. So we have these oscillations and like the high frequency stuff inside our inputs, and they started polluting our motion predictions. I'll show that in a bit, but basically that is what led us to look for alternatives to do this mapping. And therefore, we proposed this feature-encoded training. So the feature-encoded training is basically a method to map the basis coefficients of our sEMG signals to the basis coefficients of the motion. The way we do this is we take the EMG signal from each muscle, we project it onto a low-dimensional space that contains Fourier terms and some polynomial terms, and we obtain the basis coefficients. So these A, B, and C's that you see, these are the input basis coefficients from one muscle. So we can have, for example, an A type of muscles So for each muscle involved, we obtained these basis coefficients. And we do this decomposition also on the motion. So we obtain our set of output coefficients, F, G, and H, and we have this corresponding output. And we do the mapping on them instead of mapping at each time point. Now, after obtaining the FGH, we can reconstruct the motion because we have an equation for it, and we plug it into the residual. And because we have like an expression for it, we can take derivatives analytically. And both, the method remains the same as the time domain for the optimization. We have a term that minimizes the data error, so minimizes the error between the output coefficients, and simultaneously also minimizes the residual for the differential equation for the motion. Now, this really changed quite a lot our results. So, I mean, it's pretty stark, the difference. The first column contains results of the angular motion and the angular velocity from our time domain testing predictions using the real world subject data. So you can see that when we predict, it sort of captures the mean behavior of the motion, but the oscillations are just too much. And that obviously pollutes the derivatives also. But once we switch over to the feature-encoded method, we see that these oscillations are sort of filtered out, and we get a very smooth predicted motion from our input. And likewise for our angular velocity, which is the derivative of this. And that can also be quantified by looking at the mean squared error and the R2 score. So like the closer the R2 score to 1, the better the model captures the variance in the in your data. And we see that between case 1 and 2, and also for the angular velocity. And it was also good that the estimated parameters for the subject was also within the physiological range for a human. But like, even though this did a pretty good job, there are still a certain set of limitations that we needed to address. So the first limitation we had was we were working with a very limited training data set. So we had basically 3 trials, which were, between which we need to train and also see the accuracy of the predictions. And even though the feature-encoded training did a very good job in testing predictions, we could only do so in this form of the method if the entire signal was obtained a priori. So therefore, if we need to predict motion in real time, we needed to make some modifications to the training algorithm. So our objectives then changed towards trying to improve the accuracy sorry, of the time domain training, and also try to extract maximal information from this limited training data that we have. So the first step towards addressing that was in looking at data through the lens of multi-resolution. So we wanted to represent our data by looking at those signals at multiple scales using wavelets. And just as a brief recap, any function can be represented at a scale j by looking at its coarse scale approximations at the scale before that, j-1, and also the details at that coarse scale. So basically, that means that if we're given a signal, a raw signal, and that we denote as d0, we can decompose that into its coarse scale approximations at scale -1 and its details at -1. So if we just add the two together, we obtain the original signal back again. And the cool thing about this multi-resolution technique is that you can keep on doing that until you reach, for example, for your purposes, if you need to denoise a signal, you can remove the noise up to the user requirement, and you can obtain a smooth signal that was actually hidden behind all of these oscillations. So basically, you do this by projecting the signal f onto a scale. So we can, like I mentioned, we can do that by projecting the function f onto a scale j-1. And this is a detail projector, and the approximation projector uses scaling functions, and the detail projector uses wavelet functions. So together, we can use this mathematical tool to represent data at various resolutions. This was a method to look at the data. How about our machine learning algorithm? For this, we basically turned in towards gated recurrent units because we wanted to utilize the history information to improve our prediction accuracy. So we used GRUs for that. And using certain history steps, so for example, for our motion, I think we used 4. We could minimize the data error and also the physics residual. If I didn't mention before, beta is like the penalty parameter. Yeah, minimizing the two simultaneously led us to obtain the neural network parameters and the musculoskeletal parameters simultaneously. So the platform for its physics part was more or less the same, where we had our model with the bicep and the tricep. We use the same set of subject data with its motion capture and its muscle excitation signals. But the change was that to each of these signals, we applied the fast wavelet transform, and we decomposed the signals into its various approximations and details for the input from the bicep and the tricep, and also for the joint motion. I'll just talk about how we trained our neural network using this set of data. So the way we wanted to work with this data at multiple resolutions was to train the network sequentially from coarse to fine scales of the data, right? So, for example, if I say I'm using a 2-scale training, what I'm actually doing is for the input and the output, I start my network training at the scale -1 for the input and map it to the output at scale -1. I let the network train until a sufficiently low loss has been obtained. And then I transfer the weights so that I can complete the training at the original scale. So for the input and the output, I then complete the training at scale 0. So it is important to highlight that the training finishes at the original scale, and therefore your trained model can predict the data using just the original scale of the data. So if you want to do a testing prediction to look at the generalization ability, we can just plug in the original scale of the data. We don't need to decompose it at different levels. So this was 2-scale training. 3-scale training, on the other hand, would be, okay, I start my training at scale -2. For the input, I map it to the output at scale -2, transfer my weights, continue my training at scale -1, and then I transfer my weight and finally finish this training at scale 0. So we map, we finish our training at the original scale of the data. So again, the testing predictions are made at scale 0. They're not made at other scales. So the idea here is that when we do this level by level or scale by scale training, the optimizer starts to reach a better initialization state for the training data with the fine scale details. So basically, wherever it stops here, it should give the data which has more details added to it a better start for its optimization. And if I say one scale training, I just mean that I'm training at the original scale. So when I show you a comparison, it would be 1 scale, 2 scale, 3 scale, and so on. Yeah, but basically this is how we combine the multi-resolution approach with a physics-informed RNN approach. And we, like as before, we had the same set of data. We had trial 1 and trial 3 for training, and trial 2 was used for testing. These were the inputs, and this was the output. What I'm going to start with is the testing prediction for 1 scale training. And again, only the original scale of the data was used, and decomposition was not used for training and testing here. So as you can see, it starts to get certain aspects of the signal, but there are still a lot of error towards the middle and the end of the signal, right? Let's bring in the next scale. So we start at scale -1 and then continue and finish at scale 0. And we start to see subtle improvements to our prediction. So this was done over multiple seeds, and the results shown here are like, this is the sort of the mean prediction, and this is like the standard deviation. So we see that the part where we had errors in the middle and towards the end, they're starting to move more and more towards how the data actually represents the motion. Let's add another scale to it. And we see the predictions getting better and better. And if we add another one, the fourth one where I finally stop, that the prediction with 4 skills is much improved as compared to the initial prediction that we started with. So basically, if you train with the multi-resolution training, it leads to a significant improvement in our testing predictions. So we wanted to also look at our parameter identification, and they were well within the estimates from literature. But what was interesting was when we started to sort of quantify our test metrics. So if we look at the normalized mean square error and the R2 score post-training, we see that it starts at around 0.6, but ends at somewhere close to 0.9, and that's pretty huge. So the test metrics overall, if we just like plot them out, if we quantify them, they improve by over 40%. And when we started to think why, one potential explanation was that maybe with this sequential learning scheme, it just introduces more variance into the learning and reduces the bias that it develops by training at just the full scale of the data. And another thing to note was that for all these scales, the same number of training epochs were used. So it's also computationally efficient because you get like a higher accuracy within the same number of training epochs. And that's also quite advantageous. So to summarize my work, we basically started with the time domain. That didn't work as we saw. So we developed this feature-encoded training where we encoded the data into a set of Fourier and polynomial bases using feed-forward neural networks. And that could successfully map basis coefficients of the muscle excitations to the motion. But there were certain limitations which we tried to address using the multi-resolution training that decomposed the input and output time series into multiple resolutions. And from data at the coarse scales, we could start mapping them at that scale and move towards mapping them at the fine scale. And this can be done sequentially using transfer learning and also using recurrent neural nets to capture the history information. And we saw that with each additional scale, there was an improvement in the accuracy of the prediction. And we think that this is because it reduces the bias and increases the variance in the training data set, thereby improving the generalization ability. So that brings me to the end of my talk. And I'd like to thank a lot of people for it, specifically my group at UC San Diego with my advisor, Professor Kai-Chi He and Dr. Xiaolong He, who both helped a lot in coming up and discussing these ideas with me, and Professor Kenneth Lowe, whose lab provided us with all of this motion data. So with that, I can take any questions that the audience may have, and I'll try to answer them to the best of my abilities. So thank you.
Thank you very much, Karan. That was very, very interesting, and always nice to see applications, real-world applications as well. So I'll open the floor for questions. If any of you have any questions, please feel free to do so in the chat, or you may also ask in person. In the meantime, I do have a question. Karan, I was wondering if you could maybe spend more time talking about the projection, but you mentioned that when we're looking at the dynamics for per muscle, you said that you're projecting them onto a lower dimensional space. Can you give more information behind that? So like what kind of projection was this?
So are you talking about this one?
Yeah.
Yeah, so basically it's just we minimize the mean squared error between the data, and we basically started with a set of Fourier terms. This was a bit of a hit and trial approach where we can set how many terms we want in our projection into the Fourier series, and we added these polynomial terms to account for the boundary effects, because towards the end of our signals, the boundary parts were not being captured properly. So we included these polynomial terms. And once we had this set of Fourier terms and the polynomial with it, we could just minimize the error between the data and this term to obtain the coefficients, the A, B's, and C's. And likewise for the motion, we also minimize the error and obtain the F, G, and H. So like we just used our real world data and like tried to map it to the Fourier and polynomial term.
Thank you. I do have a follow-up question, but I'll wait. There's a question. Sure. I cannot seem to see the chat window.
Maybe I can read it.
Oh, okay.
So we have a question from the audience. The question is, how well does this model scale to a practical scenario for real-time prediction?
So we worked with a very limited set of data, but the predictions were like, once you train the model, the predictions are almost instant, right? Because we don't need to do any training. We just plug in, it does its feed-forward process, and we obtain the motion for the corresponding motion. So if we are to get like enough data to work with, we can get these predictions almost instantaneously if we can do them for a wide range of motions and perhaps more muscles involved in the in the motion. The training will take its time, but once the model has been trained, the predictions are instant. So this I think this would be a good practical application once we get enough data to work with.
So we have another question. Thanks for that, by the way. We have another question from Alexander. What are the trials you trained on? Do they imitate the same motion, or are they different?
Right. So for now, we started with just elbow flexion and extension because it was like a proof of concept that this can work. But we do want to work with a wider range of motion. And like I mentioned, if we can, that would entail changing the equations to model to account for different degrees of freedom. We haven't done that yet, but that is also something we are looking to do. So it's just, right now it's just elbow flexion extension. So picking up a shopping bag and dropping it. So yeah.
All right. So I hope that answers your question, Alexander. We have another one from Hamza again, who says, very interesting. Would it be possible to extend this to control for things like prosthetic limbs, for example?
Actually, yeah. So that's where my motivation started with, because I feel like we can use these for prosthetics and things like exoskeletons, because we need to be able to do the motion, the predicted motion of those limbs and exoskeletons in real time. And I believe that machine learning algorithms can supplement can supplement the physics to it by increasing the speed which we make these predictions. So definitely prosthetic limbs is a very good application, would be a very good application of this method.
Thank you very much. So Philip asks, thank you very much for your presentation. Could you please explain a bit more where and how the physical model enhances your machine learning approach?
Oh, right. So actually, when we started, we were only minimizing the data, and that itself could do a pretty decent job. But to really so we also wanted to see if we can get those parameters that I was talking about. And for that, we wanted to include the physics into it, because otherwise there was no other way into it. And we did, like, I don't have those results here, but we did see like an improvement in the accuracy by including the physics term into it. But yes, you could also just use the data and use these the data minimization and use these approaches to 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 work with. But adding this physics term does enhance the accuracy a bit, and also like if we can include a more physiologically representative equation. We started with a very simple model. The parameters that we would get would also be a bit more reliable, and that would also enhance the reliability of this model.
So on that note, if I can squeeze in a little question myself,
yeah.
We do have another question, so but I'll squeeze this one in because it's related. So this is based on the incorporation of physics and pins. Can you comment about the stability of the model? So with regards to like initial conditions.
So actually, we did not face a lot of problem with initial conditions, but we did face a lot of problems with convergence with the physics term. So, and that's where this beta parameter was the culprit, like trying to balance out the data and the physics terms. So a lot of the times, if we did not have this beta within a particular range, the physics laws would just go off, and that's a pretty common phenomena. So a lot of our efforts were towards finding this range of beta. Initial conditions were fine, but it was more like, as you can even see in our synthetic predictions and in the like in our training predictions, the initial conditions are actually fine, but was more in trying to find out this beta so that we could get like a stable loss. We did this by looking at the units. So because our units here are in radians, and here they're like in acceleration terms. So if we can balance out the units, you get like a certain range for the beta, and that helps in balancing these two terms apart. So that helped us in solving that instability in the loss.
And on that,
Sure.
so thanks for the reply. On that, what about the relationship between the trade-off between the representation of the dynamics in the data and the physics? So basically, how much data you need versus how much physics you need.
So we, like, each signal had about 500 points. This is synthetic, but I'm talking about like the true data. We did not do that sort of test between how many data points we need as a minimum to be able to capture all of this information. But that's a good point. We probably should also investigate that. Yeah, I don't have an answer for you for that.
That's okay. So by how much data I don't mean necessarily how many data points, but how representative. So how much what coverage of the dynamics do you need to kind of represent in your data set such that your model is able to extrapolate or make up for the parts of the physics. So the goal, I guess, is the physics is meant to kind of make up for the missing physics in the data. So that's sort of I think the benchmark that would be interesting to see.
Right. Yeah. But yeah, unfortunately, we didn't look into that, and I didn't even think about it until now that you asked me. But that's a good point. I should probably investigate that. Yeah. Thank you.
So I'll move on to the next question from Saba, who says, "Thank you so much for this talk, Karan. What advantage does the GRU offer over the LSTM for this specific application? This talk This talk is really interesting and offers many insights because for my undergrad project, I've been trying to get an LSTM RNN to work on interpreting electrical impedance tomography data, but have many reliability issues. So I will give GRU a try." So just to reiterate, the question was, what advantages does the GRU offer over an LSTM for this specific application?
So actually, we just looked at the GRU. We did not look at the LSTM. I'm not sure if I can answer that question accurately, but I would say you could probably do the same thing with an LSTM with what I did with a GRU. The differences between them, I do not know like off the top of my head, but we just used a GRU for this problem. We could use an LSTM also for all of this. The crux of this idea was this multi-resolution, because you can decompose the data and then use any sort of network you want that fits that fits your problem. So I don't know if an LSTM would be better or if a GRU would be better, but yeah, that would be a good thing to find out.
So thank you very much. We have another question from 718481. Thank you very much for your presentation. I'm very interested. Can your research be used in equipment health assessment and prediction, or build a digital twin for device health prediction? Any applications in the asset maintenance or management domain? Thank you.
Right, that's a good question. Like I mentioned, I think like the goal of our work was to be able to create a digital twin, and it certainly could be used. We need to define certain metrics for the health assessment for it, for sure. That was not in our scope. We just wanted to be able to predict motion, and that step is next. But in regards to using this for other things such as asset maintenance or asset management, I would assume that would be possible if we have an input and output relationship in your asset, which sort of mimics or imitates this relationship. I'm sure we can use these methods along with the physics of that asset to be able to do any sort of assessment on it. Yeah, we just need to define the metrics.
Okay, thank you very much. So I have one more comment to make, and
Sure.
because the nature of your data sort of seems also like a very suitable application for things like modal decomposition methods. Have you considered these kind of methods for learning for doing this decomposition of frequencies and modes, and then building simpler models that could reconstruct in a Fourier fashion the final signal?
That's a very good comment. We started thinking about that, but we stopped at a point because this was more geared towards like a human MSK system. But I think that's a very good, that could be a very good application of this sort of method to decompose the solution using the model decomposition. But yeah, we haven't done that yet, but that would be a good application to it.
Yeah, it might help like with interpreting as well, with interpreting the modes.
Yeah,
but I can also do that in a way here as well, potentially. Okay, so do we have any more questions? I don't think so. Thank you once again, Andrea, if it's all right with you, I think we'll maybe call it a day here. So, oh, Sava, you're welcome. Are you there? So asks if there are any in-person talks planned in the future. Well, it's hard to say. Most of our speakers are connected remotely, but we do hold hybrid talks. So if the attendance is not too large in person, we can potentially accommodate a few people. But yeah, it would most likely be a hybrid. So the speaker would be online, but we will discuss internally and see if we can maybe organize in-house, in-person, talks.
Yeah, I mean, on this maybe, I mean, the seminar series started, I think, during the pandemic, actually. So that's why we optimized the format for, I mean, for online attendance. But yes, like sometimes we will also have in-person things and we will advertise it. Yeah.
Yes, of course.
Yeah.
All right. Thank you very much once again. Thank you very much, Karan. Thanks for sharing.
Thank you, Michael, Andrea.
If it's okay with you, we will contact you in person to make it more formal. We would record this. We would share the recording on online on our YouTube channel. Okay. Then we will come. We will.
That'd be great.
Fantastic. We'll come back to you in a bit with that. But to the rest, the recording will be available on the same webpage as the talk advertisement. Thank you, and see you for the next session.
Thank you. Bye.
Bye.